Welcome to Unit 2. In this unit, we'll address probability and, more specifically, the normal probability distribution. Let's start out with the basics. What comes to mind when you hear the word probability? Now, most people think of gambling. I mean, Vegas. What are the odds if I bet on this race, if I bet on this game of cards or whatever? What's my chances of winning? A lot of times people also confuse payoffs with odds. Just because the house pays a certain way, that doesn't mean that that's the real odds of you winning. Because remember, the house is there to make money, so they have to keep an edge. And you bet on horse races, and you notice that the payoff changes as more people bet on a specific horse or fewer people bet on a specific horse. So that's not really the likelihood of anything happening. The true likelihood, well, if you were to roll a six-sided die, the odds or probability of rolling a 2 is 1 out of 6, simply put. And, of course, it gets a lot more complicated when we put in more dice and have many cards. But it can get very daunting to try to compute some of those probabilities. That's why we have some wonderful tools that help us do it. But that goes beyond the scope of this course. It's not really about figuring out the odds of winning each and every game. Now, this course is really much more about using probability concepts and more specifically learning about the normal distribution, since that is going to be a cornerstone of hypothesis testing and pretty much everything else we do in this course. But I'd be remiss if I didn't give you a little taste of the fun parts of probability. One of the most famous probability problems, it's truly a classic, known about it for, it's probably 30 years old, if not older, is known as the let's make a deal problem. You could search for it all over the internet. I think there's about 150,000 links out there right now where you type in let's make a deal probability problem, and it's amazing what you'll see out there. Where basically, if you think to the game show that was on in the 60s and 70s, there were 3 doors and you picked a door and the host actually shows you one of the other 2 doors and that has a booby prize behind it, and then asks, would you like to keep your door or switch with the other door? And you wonder, am I better off keeping my door because you trust your first instinct? Am I better off switching? Or, well, there's only 2 doors left. It's 50-50. Well, go search for a link out there. You'd be amazed what you'll find out, and I promise it's rather deceiving. Another famous one is called the birthday problem. If you were to ask a whole bunch of people in a room, when's your birthday? Just the month and day, not the year. And then I asked you, how many people do you think have to be in the room before the odds are in my favor if I bet that there's matching birthdays in there somewhere? We know that if there were 366 people in the room, that somebody is matched with somebody. There's got to be 2 identical birthdays in the room, since there's only 365 days in the year. And I know about leap day. I'm really kind of counting that as February 28th. So if there's 366, you're guaranteed that somewhere in that room there's a match. But if there were only 360 people, I'm sure you'd still bet on a match. You're not going to believe that they all have different birthdays. At what point would you actually take the bet that there's a pair of identical birthdays in the room? Maybe 183. That's half the year. You'd be surprised. The actual number that makes it favorable to take such a bet is 23. Check that one out. That's another one that's all over the internet. And when you see it, explore it, you might still be confused, or you might go, aha! And that's part of what I love about a probability. When you start to explore stuff like this and you realize something that defies logic like that, could be so true. You wonder how the house always wins in Vegas. They don't really even have to set the payoffs the way they do, because you can actually play it straight up and people don't realize what the odds really are, and they might bet accordingly. And one other site that I would recommend you check out if you really are into the games of chance, it's called wizardofodds.com. It pretty much goes through every card game, dice game imaginable, teaches you how to play when you're playing the odds. You really don't learn about people in this. You're learning strictly about playing the odds. So it's really wonderful. So you get to actually see probability in action on so many different games. Do check it out. I think if you have a little bit of gambling in your blood, you'd really appreciate it. Now back to the course. Probability in a quantitative form, it's basically telling us, yes, the likelihood of something occurring, but mathematically what we do is we actually have to figure out how many possible outcomes there are, and then how many of those outcomes meet the condition we specify. If you were to get a standard deck of cards, which has 52 cards in it, and you were to pull one card out of the deck, sight unseen, and I said, okay, what's the probability that that card is red? Well, there are 52 cards that are possible that you drew, 26 of which are red. Probability would be 26 out of 52, 1/2, 50%, however you want to express it. If I asked what's the probability the card is an ace, there are 4 cards meeting the condition out of a possible 52. So it's 4 out of 52, or 1 out of 13, or about 8%. If I asked what's the probability that the card happens to be an ace of hearts, there's only 1 card meeting the condition out of a possible 52, so it's 1 out of 52, or approximately 2%. So basically, you need to know how many meet the condition and divide that by how many total possibilities there are in our sample space, as we like to call it. Don't jump to conclusions about fairness. I mean, if you see 52 cards, well, and you can count them, you see that there are 52 different cards, well, that's clear. We could see all the possibilities. But if I flip a coin, and I said, take a look, there's a head on one side and there's tails on the other, so it's not a double-headed coin. If I said if I flip the coin, what's the probability that the flip turns out to be heads? You might go, well, there's only 2 possibilities, it's 50-50. If the coin were fair. But if I bent that coin, it might come up heads 80% of the time. You don't know that. So don't assume just because there's only 2 there's only 2 possible outcomes, it's got to be 50-50. Just like if I said, well, my class consists of men and women. What's the probability that I pick a woman? You go, well, 50%. It's either a man or a woman. But if there's 8 men and 2 women in the class, it's more like 20%. So once again, just because it sounds like there's only 2 possibilities, that's not true. You have to look at the individuals, not not the groupings that they belong to. Probability when computed will always be a number somewhere between 0 and 1, or 0 and 100% if you choose to use decimals or percents. Same idea. You'll never get a probability less than 0%. It's impossible. It can't be negative. You'll never get a probability greater than 100%. 100% is a certainty. 0% means it's an impossibility. Most of the things that we deal with are somewhere in between 0 and 100%. But yes, there are things that are 100%. There are things that are 0%. So don't assume, you will never see that. Yeah, you will. There's many instances. It's like if I were to ask you, what's the probability that I flip a coin and it comes up spades or something like that? Well, there's only heads and tails. That can't happen. So, that happens. If I have 10 men in a class and I say, what's the probability that I pick a man? 100%. It happens. So don't assume, we can never have this and never have that. Yes, it does happen. But most things we deal with in life are between 0 and 100%, which is why we have to actually do some thinking, put some work into it. Now, if we did lay out those cards I was talking about, if I spread out 52 cards on a table, and I did it in 4 rows, so I have diamonds in the top row, then hearts, then clubs, then spades, and then I lay them out ace through king, what you have in front of you, basically it's a tableau, a table. I made it so that it's suits going down the side, values going across the top, and you've got 52 cards spread out very nicely. In doing so, you set yourself up to really easily compute probability with just drawing circles, very, very easily using a tool we grew up with called Venn diagrams. If I were to ask you what's the probability that the card you draw happens to be a 2, you could just circle the 4 2s and go, there's 4 2s circled, and there's 52 total cards, 4 out of 52. And if I said what's the probability the card happens to be a 2 and a heart at the same time, 2 of hearts. If you circled all the 2s and you circled all the hearts, you'd notice that there's an intersection. The 2 of hearts intersects both of those circles. So the answer would be 1. Why? Because based from rules of set theory from when we were kids. You did that in the beginning of every math book, it seemed. When you're asking for the probability of two things happening at the same time, you look for the intersection of the circles. Well, we're going to actually apply that principle right now. If you look on the slide, you see a table that I made up, so don't read into this, it's just numbers. I asked 60 women and 40 men what political party they're registered with. And you could see the numbers in front of you. Well, imagine I threw 100 names into the hat and I randomly pick one out. What's the probability the person whose name I randomly chose happened to be a female? Well, there's 60 women in the group, so it would be 60 out of 100. If I circled all the women, it'd be really easy to figure that out. And the probability the person I happened to pick would be Republican would be 45. I randomly, I circled the 45 people and there's only 45 meeting the condition of Republican. But if I said female and Democrat, well, that means they have to be both females and Democrats at the same time. So if I circled all the females and I circled all the Democrats, according to the set theory rules, when you're asking for two things to coexist, basically an and condition, you are looking for the intersection. The person has to be both female and Democrat at the same time. 30 people meet that condition out of 100, 30%. If I said the probability the person's a female or a Democrat, the word or means it could be either one or it could be both at the same time. So that means the person could be female and anything else. The person could be Democrat but not a female, meaning male, of course. Or the person could be a female and a Democrat at the same time. So if I circled all the females and I circled all the Democrats, I would see a 10, a 30, a 20, and a 10 all in some circle or another. 70 people are in either one group or in the other group or in both groups at the same time. 70 out of 100, 70%. What I did was I computed what was called the union. In set theory, when we were asking for an or condition, which means you're one group or the other or both, we actually add up everything that's in either circle. We don't double count anything. We just say anything that's contained in a circle, one way or another, throw them in there. And so we're computing what's called the union of the sets. That's how we end up with 70 out of 100. The only people that don't fit the bill are the male Republicans and the male independents. The next one shows probability of a female, and it says, then it's got a slash Democrat. That's our statistical way of stating given. That means being a female, given that we know the person is a Democrat. We know for a fact that that person is. Given that's the truth, now what's the probability? Well, what that means is if we know the person is, we can block out the other groups. We don't even have to look at the Republicans and Independents in this particular instance. We say, okay, we're dealing with only 40 people. It's got to be from those 40 people. And of those 40 people, 30 are females. Notice that it's no longer out of 100 because when I do given, I've eliminated the other groups. Think back to cards. If I ask what's the probability the card I happen to pick is a heart, you'd say, well, 25% of the cards are hearts, so it's 25% or 1 out of 4. Great. If I told you in advance the card I'm looking at is red, you'd say, whoa, if it's red, it can only be diamonds or hearts. So now there's 13 hearts, but it can only be out of that 26. So now it's 50%. The probability is different. Of course, now if I flipped it around and said, I'm guaranteeing the card I'm holding is a heart, what's the probability it's red? You go, well, it's got to be red if it's a heart, so it's 100%. Yes. Notice how asking what's the probability that the card is a heart if I know for a fact it's red, 50%. What's the probability the card is red given that I know for a fact it's a heart, 100%. They're not the same question. When I reversed it, they're not the same question. It would be like asking, hey, the person I'm thinking of in this room is a male. What's the probability the person has a mustache? And you go, okay, let's look at the men who have mustaches. If I reversed the question, I said the person I'm thinking of in the room has a mustache. What's the probability the person's a male? Completely different question, as you can see. So on the last one here, back to the political one, it's got probability of Democrat given female. Well, in that one, I only look at the row of females. there's 60 females. Of the 60 females, 30 are Democrats. So 30 out of 60, 50%. So you could see probability female given that they're Democrat, 75%. Probability Democrat given that they're female, 50%. Not the same question. Sometimes by coincidence you get the same probability, but these are not the same question. That brings up another interesting issue. Let's say a person was getting a medical test done for cancer. And it turns out that this test, the doctors tell you, is very accurate. If you have cancer, you can pretty much count on it will test you positive. If you don't have cancer, you'll test negative. It's not perfect, but it's 98% accurate. 98% accurate because 98% of the people who have it test positive. 98% of the people who don't have it test negative. Well, that's great. Sounds like a perfect test to me, or close to it. Except, you just had a test done and you tested positive. Question is, what's the probability that you actually have cancer? Do you think it's 98%? Do you think it's at least 50%? Well, you'd be surprised to learn it's not only not either of those, it's a lot less than 50%. Yet you tested positive. How can that be? The test is 98% accurate. Yes, 98% accurate, meaning if you have cancer, you will almost certainly test positive. But that's not the same as if you test positive, you almost certainly have cancer. Remember, red cards might be hearts. Hearts must be red cards. They're not the same question. What happens here is we'll try to imagine in the world that only a small percentage of people have cancer. To use numbers, let's suppose that there's 10,000 people and only 100 of them have cancer. Okay. Of the 100 people who have cancer, 98 of them will test positive, okay, because the test is 98% accurate, and 2 will test negative. So 2 people got told wrong that they don't have it when in fact they do. Of the 9,900 who don't have cancer, 98% of them will test negative, but 2% of them will test positive by mistake. And 2% of 9,900 is 198. These people are what we call false positives, a real common expression in the medical world. So now let's take a look. 10,000 people. Of those 10,000 people, we have 98 people who have cancer and tested positive correctly. We have 2 people who have cancer and tested negative incorrectly. We have 9,900 people without cancer, and of that group, we have 9,702 who tested negative correctly and 198 who tested positive mistakenly. So let's reverse the question. Which people tested positive? Well, we have 198 and 98. We have 296 people who actually tested positive, 98 of whom actually have cancer and 198 who don't. So of the group who tested positive, only 1/3 actually have cancer. A test that's 98% accurate, saying if you have it, you will test positive, and yet if you test positive, there's only a 1/3 chance you have it? Doesn't make it a bad test. Actually, it isn't a bad test. It does mean you should get a second opinion, do another test if you test positive. If you test negative, you should feel pretty darn good because you don't see too many false negatives. But if you test positive, it's a good chance, and I mean a better than 50% chance it was a mistake. So have another test done. Have it checked again. I've seen it happen before with people. And that kind of gives you a different look at conditional probability, the misconception of what it means for something to be accurate. And if that doesn't make you think, consider that that's a 98% accurate test. Pap smear tests, when I read them last, were rated as only being about 75% accurate. Think of the false positives that come out of that. Lie detector tests were rated as just under 50% accurate. That test has so many false positives, you can imagine why they can't admit them in a court of law. Now let's move on to the normal distribution. Now, I know it's the word normal. You might wonder, does Does that mean everything else is abnormal? No. I don't really know why it was called the normal distribution, but it really was found by a man named Gauss. It's often referred to as a Gaussian distribution, but we kind of like using normal. It's much simpler. Students actually remember it a lot better. So it's the bell-shaped curve that you've probably heard so much about your entire life. And yeah, that curve again, here's that word that years and years of teaching, even being a student, and you hear about teachers grading on a curve. What does that mean? The bell curve that they talk about. You've probably been on the receiving end of curves many times. In fact, you've probably begged teachers at one time or another to please grade on a curve. You better be careful what you ask for. You just might get it. Grading on a curve is not what you think. True grading on a curve means following the normal distribution. That means that, the people score, that somebody, the ones in the middle basically, are going to be at the peak, and you're going to have some above and some below. I'll go into that in a second, so you can really grasp what the true meaning of grading on a curve is, and why you might be glad that you didn't always get what you asked for. If you were to look at somebody, let's say a 5'8" person, and I say, is that person tall? When you're judging that person being tall or short, you're probably looking at whether the person is male or female. A 5'8" male is considerably middle, maybe medium to short. Average male height is close to 5'10". A 5'8" female is considered tall. In fact, she'd make the basketball team without question. 5'8" man wouldn't have a shot. It's all relative, but we judge relative to the average of the group we're dealing with. So we would always put that one in perspective and say, well, we know the average is here, and we're asking about this, and this happens to be bigger than the average or smaller than the average, and by how much. Or if I were to say, is $50,000 a year a good salary? I mean, can you really answer that? If you're thinking about for yourself, you might say, well, no, I've made a lot more than that. But if I haven't qualified it yet. If I said, for a person who's a receptionist, you'd say, oh my God, that person's making a fortune. Because receptionists require no education whatsoever and typically don't do much better than minimum wage. So $50,000 for a receptionist is way, way, way above average. If I told you the person was a professional football player, you'd say, oh my God, he's getting ripped off. There's no way. Football players should be making at least $250,000. Something's wrong with that, so that person's making way, way, way below average. Yes, you've got to put it in perspective, and we compare to the norm. So we're always taking whatever we are asked about and comparing it to the norm, and then considering how far above or below that norm is. And we like to use the mean as that norm. What we're actually doing in this unit is computing something called a z-score. Z as in zebra. It's simply computed. We're just taking the distance from the mean, positive or negative, and dividing it by the standard deviation. Because just saying how far above or below, that doesn't help enough. Because what does it mean to say I'm making $10,000 above average? Well, $10,000 above average in a world where you're dealing with salaries of $20,000 and $30,000 is monstrous. $10,000 above average if you were dealing with baseball player salaries in the millions is minuscule. So you have to know what the spread is like. So the z-score is simply the value minus the mean and divide by the standard deviation. You're going to get numbers typically in the -3 to +3 range. In fact, if you take a look at this chart, you see that with a normal distribution, the bell curve, you'll notice that scores in the -1 to +1 range account for about 2/3 of all the data. It's more specifically, 68% of the data falls in that range, about 34% on each side of the mean. If we were to go between -2 and +2, we get about 95%. If we were to go between -3 and +3, we get 99.73%. A lot like what we saw in the first unit when we looked at the descriptive statistics chart. If you remember where it said mean plus or minus 1 standard deviation, plus or minus 2, plus or minus 3, and I had those computations there, that essentially is what the normal distribution is doing, is showing. So we expect to see most of the data in the middle and less data further away. And after 3 standard deviations, you just don't expect to see too much. Now, many of you have probably taken the SAT or the GMAT. And if you ever wondered, what's the scoring system like? What really goes into this 800-point scale where you go from 200 to 800 on the math and 200 to 800 on the verbal? How did they come up with that? What's a good score? Well, that can all be explained by the normal distribution. They compute your raw score based on the number of questions you answered correctly out of how many they actually had. And there's usually a few throwaway questions that are there just for testing purposes from them that they don't really count toward your score. And they penalize you for wrong answers and whatever, and you come up with some raw score. And they take all the raw scores, and they compute the average of the raw scores. Whatever average there is automatically becomes a 500. They compute the standard deviation of the raw scores, and they check each score relative to the average, and basically they compute a z-score. So let's suppose that on the math SAT, the average raw score was getting 50 questions correct, and the standard deviation was getting 10 questions correct. So if you got 50 correct exactly, your score would be 500. If you got 60 questions correct, your score would actually be 600, 1 full standard deviation above the mean. If you got 65 questions correct, you'd be 650, 1.5 standard deviations above the mean. But what they do is they stop it after 800. If you're 3 or more standard deviations above the mean, they just leave you alone at 800. Going the other direction, if you're 3 or more standard deviations below the mean, they stop it at 200. Kind of an off-the-wall system, at least it sounds that way. But in their thinking, if you got the average score on the math and the average score on the verbal, 500 and 500, your score would be 1,000. It's basically what they came up with. Scores of 1,000 or more basically means you scored above average overall. Scores below 1,000, you scored below average overall. So your total between the math and the verbals would range from 400 to 1,600, and 1,000 puts you right on average. So once you hit the 4-digit numbers, you know you broke the average. But taken independently, each one has an average of 500, standard deviation of 100. It's all standardized. So once you know your score, you can actually backtrack and figure out what percentage of people you beat. So if you scored 700 on the math SAT, you were 2 standard deviations above average. In essence, you beat about 97.5% of the people who took the test. Likewise, if you scored 800, well, you're in the top 0.27%. We don't know exactly because they stopped counting after that point. You scored 200, you're in the bottom 0.27%. Doesn't mean you got every question wrong, but it does mean you were 3 full standard deviations below average on that test, regardless of what your score happens to be. Now let's go back to the grading on a curve. Now every instructor may veer a little bit from this, but traditionally what grading on a curve would mean is the score that was the class average, well, that is the mean, that becomes the cutoff for a B. Because if you scored above that, you were above average. And 1 standard deviation, for most people, is the cutoff for an A. So if you scored 1 full standard deviation above average, you got an A. And they'd go the other way. Up to 1 standard deviation below the average gets you a C. Up to 2 standard deviations below average gets you a D. And beyond that would get you an F. And wherever your grade falls, it falls. You get the grade, you get the letter grade that goes along with it. So is that fair? Well, and who gets hurt by it? Who helps it along? Who's really the curve killer in that particular situation? Growing up, I remembered hearing people would basically go after whoever did the best. You ruined the curve for everybody else, would be the chant. I know I didn't do well on the test, but I would have gotten a better grade if you didn't take the test too. Well, would you be surprised to learn that it's not that top student that's destroying the curve. It's the bottom student that did it. They're the ones actually that are killing the grades for everybody else. Now, people are typically on the bottom end they don't really feel it. Either they're failing anyway, or they might get bumped into a passing grade. But they either got what they deserved or better than they deserved anyhow. The people on the top, they have nothing to gain by the curve and everything to lose in many cases. And often that's what happens. So let's suppose an exam is given and it turns out that the class average happens to be an 80 and the standard deviation happens to be 10. Well, grading on a curve, the cutoff for a B would be right at 80. The cutoff for an A would be 10 points higher than an 80, which would be 90. And the cutoff for a C would be 70, and the cutoff for a D would be 60. Sounds like a really familiar grading system there. Yeah. And you would expect that roughly 34% would have B's, roughly 34% would have C's, just following the normal distribution. Roughly 16% would have A's, about 13.5% would have D's, and 2.5% would have F's, based on the system. So suppose that there's one extra exam that shows up in the pile that I just forgot to grade. Person got a 100 on it. What's that person going to do to the curve? Well, no doubt the average is going to go up, but not that much. 1/100 that's averaged into an entire class that had an 80 to begin with might raise it to 81. And maybe the standard deviation will be adjusted a little bit, so it probably will go down to around 9. So now the cutoff for a B is instead of an 80, it's now an 81. The cutoff for an A pretty much remains 90. The cutoff for a C has gone up slightly to 72. Cutoff for a D has gone up slightly to a 63. So you might say, hey, that person who got the 100 hurt me a little bit because my 70 used to be a C and now it's a D+. Okay, I can see that. It's possible. But let's look at the other extreme. Somebody gets a 2 on the exam. Thank God that person got a 2. He brought the class average down. Now the cutoff for a B, instead of being an 80, is a 76, thanks to that 2. Okay, yeah, all fair. That 76 now qualifies for a B. But what that person did to the standard deviation is destroyed it. Because instead of a standard deviation of 10, it's probably more like 26 now. Could be higher. Depends on the size of the class, of course. But let's suppose that it turns out that the standard deviation is 26. Now what? Well, the cutoff for a B is 76, yes. And the cutoff for a C, well, that's 50. Thank you. The cutoff for a D drops down to 24 points. A 24 passes the course now, thanks to that person who got a 2. And oh yeah, the cutoff for an A, 102. Now nobody gets an A. So everyone with low A's, mid A's, high A's, they all get B's because someone got a 2. And yet people who failed the exam legitimately are now getting D's and C's. Tell me what's fair about that system. But unfortunately, that's actually what goes on in a true grading on a curve. It's not giving away free points to everybody. It's basically pushing it up in the center, and everything kind of falls where it falls. And it seems like the better students don't gain much in this process. They have everything to lose, and those at the lower end have nothing to lose and everything to gain. And, you know, if you were an A+ student told that you were being graded on a curve, you would actually have to worry if one of the poor students chose not to study, because they're taking your grade down with them, making you dependent. So I know that kind of goes, it sounds like it's going off the subject, but the reality is that's the essence of the normal distribution. And unfortunately, when it's used improperly, people could end up getting burned. Now the SATs are graded on that kind of scale too, but there's a difference. Grading 1 million students on a scale like that, not really a problem. One student cannot single-handedly destroy the curve. It's going to take a heck of a lot more than that. It's going to take 1,000 students or so to do that. There would have to be a cheating scandal. But in a class of 20 or 30 students, a single score, a single outlier, can completely make a shambles out of the grading curve. So now let's look at the normal probability Excel file that you've got in your course. If you open up just the very first spreadsheet, you see a place for you to enter a mean, a place for you to enter a standard deviation, and then you can compute several probabilities. Now there are actually other tabs in this file, tabs where you can see physically what happens to the normal curve. So you could say, if I want to know the probability of something, of the value being greater than 200 versus greater than 500 versus whatever, you notice that the shaded area of the curve actually moves up and down. And what's going on is you're actually computing how much of the area is shaded red. If you assume that the entire area under the bell curve equals 100%, we're asking what percent of the area is shaded. So it's like if I drew a line right down the middle and shaded everything to the right of it, well, that's half the curve. So if I ask basically what's the probability of being better than average, it would end up being 50% because half the curve is shaded in. On the SAT, and this is the example I used here, we know the mean is 500, the standard deviation is 100. So if we asked what's the probability of getting less than 300, 300 is 2 full standard deviations below average. So that would be a z-score of -2. And if you dropped a line down at the -2 area and shaded everything to the left of it, you only got 2.28% of the curve shaded in. The other 97% is to the right of it. And it makes sense. You're that far away from the mean. There's not as much there. And if we were to ask probability of being greater than 700, you'd see the opposite part of it. But we can compute values at any range of the normal curve. We also can compute these percentage above, percentage below values. It's kind of like percentiles, where you're doing it in reverse. If I said, what score would I need to get such that only 5% of the students beat me, or that I'm in the top 5%? It shows here 664.49, which of course on the SATs they're scored in 10-point increments. So a 670 would guarantee you're in the top 5%. You could express it the other way and ask, what score do I need to get to beat X percent? So if I put being 95%, I notice it's the same score, because getting 5% of being above you and 95% below you is the same value. But you can change it to anything you want. So you could say, what do I need to be in the top 10%, the top 20, to beat 50%, to beat 75%, whatever you want to put in there, you can do it in reverse. So this particular technique allows us to solve probability problems with 2 pieces of information. If you know the mean and you know the standard deviation and nothing else, you can solve probability. Because if you remember it in Unit 1, I told you that you need both a measure of central tendency and a measure of dispersion to completely define data. And that's the case here. To define a normal distribution, the mean and the standard deviation is all you need. So if you found out, for example, that in a company the average salary was $52,000 and the standard deviation was $13,000, you could go into the normal probability file and say, okay, so if I make $60,000, where does that put me? Or what salary do I need to make to be in the top 10% because I think I'm worth it and that's what I should negotiate for? You can figure that out with just 2 pieces of information, not having to look at any other data. And I think that's pretty powerful stuff. And that's why this tool is treated in such high regard in statistics, because there's so much you can do with such little information. And all of the hypothesis tests, for the most part, are built on this distribution. Well, a normal distribution is a great tool, no doubt. But what if our data isn't normal? What if our data does not fit the bell shape? We can't rightly solve probability problems if our data doesn't look like a bell-shaped curve. Or can we? Well, luckily, there's something called the central limit theorem. This theorem basically allows us to use the normal distribution even if our data isn't normal. What happens essentially is if you take samples of data within a population, even if the population isn't bell-shaped to begin with, you take a sample, and take another sample, and take another sample, the sample means themselves will become bell-shaped. So if you can imagine a group in which, let's suppose it was a school that had 2 athletic programs. Everybody in there was either a basketball player or a gymnast, just to kind of be extreme. So we've got a lot of people who are 6 foot and a lot of people who are 4 foot tall. And no one in between. Well, that doesn't look like a normal distribution of heights. You've got just 4-footers and 6-footers, 2 big spikes and nothing else. Okay, if I randomly pick 2 people out of that group, I might get 2 4-footers, I might get 2 6-footers, and I might get one of each. And if I compute the average from my sample, 25% of the time I'm going to get 2 4-footers and get an average of 4. 25% of the time I'm going to get 2 6-footers and get an average of 6. But 50% of the time I'm going to get one of each and get an average of 5. Now if I graphed that, I now have something that looks more like a triangle. You have a bar that goes up 25% on the 4-foot, goes up 50% on the 5-foot, and 25% on the 6-foot. Suddenly it's peaking in the middle. And if I took a sample of 4 students at a time, without showing all the math, what you would end up seeing is that approximately 6% of the time the average would be 4 feet. Approximately 25% of the time it would be 4.5 feet. 37.5% of the time it would be 5 feet. 25% it would be 5.5, and then 6% it would be 6. So it's really starting to peak in the middle. And yet I've only taken a sample of 4. And as I take a larger and larger sample, we find that it starts to look more and more like a bell curve. And think about it. If I took a sample of 25 of these students, how likely is it that I'm going to get 25 from one extreme or 25 from the other? You'll almost certainly get a mix of 10 or 15 from each group. So when you average them together, you're going to end up closer to the middle than to either extreme. And that's essentially what's happening. It's the central limit theorem is basically saying as you take a larger and larger sample size, the sample mean of the means, which they call the sampling mean, ends up staying the same. The overall mean doesn't really change. But the distribution of those sample means ends up starting to look like a normal distribution. And so instead of actually doing computations based on the actual data, we do it based on potential sample means. And the sample means themselves are normally distributed. So if I look at the Excel file I've got in front of you, it looks very much like the other one with one exception, well, 2 exceptions. One is that it's now asking for a sample size. It still has the mean and the standard deviation, but now it has a sample size. And the other is in computing the probabilities, it doesn't say x less than and x greater than, it says x bar. That's the sample mean. So we're no longer asking about individual values, we're asking about the sample means. So going back to the SATs, we know the mean is 500, we know the standard deviation is 100. A question might ask, if I were to sample 4 students, what's the probability that the average from those 4 students is greater than, less than, between, whatever? So in this sheet you see what's the probability that that sample mean is less than 450. Not the actual individual scores being less than 450, but an average of 4 students being less than 450, and it shows a percentage of 15.87%. What you're going to find is that you expect greater probability that the mean would be in the middle, and a whole lot less that it would be to the extremes. It's like, could you imagine trying to randomly picking 4 people and getting an average that ends up being over 700? The likelihood of one person being over 700 is 2.28%. Try to randomly pick 4 people and get an average over 700. It's not very likely to happen because essentially you would have to have almost all of them above 700 to begin with. One might be slightly below, but you couldn't have anybody who was well below, or the average wouldn't work. The likelihood becomes very slim. So you would end up seeing larger and larger percentages toward the center and lesser as you get further away. And if you take a larger sample size, it's going to be even more like that. The important thing about this is because of the fact that we are able to treat these as normal distributions, that means that if our data is not normally distributed, as long as we're taking sample means and working with them, we might be able to assume it's normal. The rule of thumb is if the sample size is at least 30, we can guarantee it. because every test run on every kind of distribution there is found that as long as it's 30 or more, they look normal regardless. Depending on how far off the mark the distribution was to begin with, it might not take that much. If the data was already uniform to begin with, just kind of an even spread, it may only take 10 before it looks like a normal distribution. So the more obscene, the more distant from a normal distribution it is to begin with, the larger the sample you'll need to get it there. But even if you couldn't do the tests yourself, you know for a fact that 30 will get you there. Some books use 25 as the minimum. The important thing is it enables us to use the normal distribution on data that doesn't look normally distributed as long as we take a large enough sample size. And that makes this tool even more powerful. So you now have the tools necessary to move forward, solve probability problems, and also lay the cornerstone for inferential statistics. And this closes Unit 2. The next unit will be addressing confidence intervals and sample sizes, two very commonly used popular tools. Although you may not know them by name, you'll know them when you see them.